Okay, right, now we don't have very long, so I'm going to talk about the birth and death of stars. I've done this before, but I'm going to do it slightly differently tonight to perhaps give you a little bit more insight into some of the things that we see. When we look at the night sky, we're used to the idea, or we're taught, that the pattern of stars is essentially unchanging. Of course, this is only true on the time scale of a human life. If we were to come back in 100,000 years, we'd see the pattern of constellations change, and over a period of 1,000,000 years or so, we would see that some of the stars had come, and some of new ones had come, and some of the old ones had gone. Now, underlying the whole story of stellar evolution is really the story of the force of gravity. Gravity is the weakest of the forces, and yet on the largest scale it essentially defines much of what happens in astronomy. And if we think of two protons, they have a positive electric charge, so they repel each other with the electrostatic force, but they do of course have mass, so they experience gravity. But the force of gravity is, in relation to this, 10 to the minus 36 times the force of the electrostatic force. And what that means is that if we want to make a star, then we have to get an awful lot of protons and neutrons and electrons together in order that the sum of the mass becomes sufficiently large to enable us to push those protons together and get nuclear fusion going on, which is why stars are so large. Now, the story of the origin of stars and the origin of the elements, well, it goes back to the start of the universe, but we'll pick up the story when the universe is a second or two old. From when it was about a millionth of a second or two old, it was full of the protons and neutrons and electrons that are the building blocks of the elements as we understand it. When the temperature was about 10,000 million degrees, at about 3 seconds old, for a while hydrogen, which we might refer to as protons, fused together for the next 3 minutes or so to form helium. And after about 3 minutes, when the temperature had dropped to about 1,000 million degrees, this nuclear fusion reaction came to an end, and we ended up with about 75% hydrogen and 25% helium by mass, and that is very much the way the universe still is today. Time went on, the universe continued to expand, continued to cool, and the next great key moment came when it was about 300,000 years old, when the temperature had dropped to about 1,000 degrees, and the electrons got together with the protons, and the gas, the plasma, the hot plasma became neutral, and photons were therefore allowed to travel in straight lines unimpeded thereafter. And of course, it is from that time that we observe the familiar, famous microwave background with its incredibly subtle variations in density, which later on were to become the structures, the things that form galaxies, clusters of galaxies, and of course, individual stars. Time moved on, the universe continued its expansion, and it continued cooling. And we entered what astronomers call the Dark Ages. And Dark Ages refers to the fact that if we had been around in those first few million years or so and looked about us in the universe, it would have appeared completely dark because there were no stars, and it was now too cool to be self-luminous. Dark to the human eye, but not, of course, dark at all electromagnetic wavelengths. And in fact, stuff was happening. Those small density fluctuations were drawing matter together, concentrating matter. The force of gravity was working on them. And at the end of the Dark Ages, suddenly the universe bursts back into light at about an age of 600 million years or so, and the very first stars are born, and this is an artist's impression of what that time would have looked like. Stars much more massive than the stars we see today, because they were built out of pure hydrogen and helium, They were capable of maybe being as large as 1,000 solar masses. They would have lived very short lives and exploded as supernovae, perhaps created the black holes that form the seeds of the galaxies that we see around us today. But after that moment, when the first heavy elements were made and mixed into the interstellar, intergalactic medium, contaminating the hydrogen and helium, we went on to produce stars very similar to the sort of stars we produce today. And that brings us into the present era, and when we look around the nearby universe, we see situations like this, one galaxy silhouetting another, and instead of seeing the conventional spiral arms of stars, we see spiral arms of dust and gas. That dust and gas that is the basic building blocks of new generations of stars. In this detail here of a galaxy, you see the 100,000 million stars, or some of them, and these dense regions here, mainly hydrogen and helium, but of course contaminated with a smattering of heavy elements. And these places here, close to the spiral arms, with these luminous red glowing regions, are places very similar to this where stars are currently being born. And this is a region in our own galaxy. Some of you may already recognize it as being this self-same region observed with a modern ground-based telescope, and here seen with the Hubble Space Telescope, this familiar feature referred to as the pillars of creation. Now, I don't like the word pillar. Pillar implies something that stands foursquare on the ground. There is no up or down in this diagram here. This thing is self-gravitating. It is drawing together under its own gravity. And as it draws together, it is being eroded by the intense ultraviolet light coming from these newborn stars that are effectively ionizing, if you like, evaporating this feature, and you see these hazy streams of material streaming away from this object. This thing is about a light year long, and if we zoom in on the top here, we see a region here that will shortly become a new solar system, these places where the density is high enough to resist the surrounding radiation, and the gas is collapsing under gravity. And let us now just look at a simulation of what is going on in that cloud. This simulation is 1,000 solar mass. It's about 1.5 light years across, and in the computer it is collapsing under gravity, and we are seeing a sort of 500,000 year history of what's going on here. You'll see it's quite turbulent, so it doesn't just collapse to one point. Each individual blob of gas collapses to form individual stars, and we see the stars beginning to appear in this simulation here. And what I want to do is just say something about gravity, because we can understand what's going on in very simple, straightforward terms. Now, as you know, mass creates gravity, so the gravity creates within an extended field of mass something that we refer to as gravitational potential energy, and that energy is interchangeable with kinetic energy. And I just want to illustrate that for you very briefly. So here I have a bunch of keys, and I'm holding them up against the force of gravity due to the Earth, the gravitational field of the Earth. And I can put the keys down on the table, and as I pick them up, I'm doing work against the force of gravity. I'm increasing their gravitational potential energy the higher I move them up above the table. And if I release the keys, what happens? The potential energy is turned into kinetic energy, and the keys fall to the table. They make a loud bang when they hit the table, as the kinetic energy is turned into sound and slightly heating the surface of the table. Now, the great thing, and that is essentially what's going on in that collapsing cloud, the potential energy being turned into kinetic energy. Now, of course, the kinetic energy of the falling keys is the same sort of thing as the random movement of atoms in this room, molecules in this room, and we refer to that sort of kinetic energy. We measure it in terms of what we call temperature. It's just the effect of individual molecules racing around with various kinetic energies. And the great thing about matter is that it has photons. Matter and photons interact with each other. That's why we see stuff. That's why you can see me. And the photons have the ability to carry energy out of the system. Energy is always conserved on the larger scale, but they carry energy out of this system, so this system can change. Stuff can happen. The cloud can collapse. And that, just since I know you're a pretty sophisticated audience here, is the fundamental difference with dark matter. Same sort of thing, gravity, dark matter creates a gravitational field, and we could have this interchange, but there are no photons to carry the energy out. So unlike the material of our collapsing gas cloud, which we see here, we are not able to radiate energy from the stars that are forming in this cloud. So as that simulation runs, the temperature drops, and the energy density drops, the energy is radiated away, allowing the stars to form. And so if we think of the process of star formation, if we think of what, let's just let this thing run through to the end, it's rather a beautiful simulation. You will see individual stars interacting with each other and being expelled from the cluster that is forming. And so let us think what a star actually is. And let us think about the actual detailed process of what's going on here. Here's a picture of the sun. The sun, it's just a sphere of gas in what we call hydrostatic equilibrium. And what has happened is, as the gas cloud collapses, the pressure, the potential energy is turned into kinetic energy. That is, the temperature of the gas rises, and that creates a pressure that resists the squeezing of gravity. But because there is a raised temperature, photons are emitted, so the gas cools, allowing the gravity to go on, squeezing and squeezing the gas to a point where the force of gravity then now becomes so great because the mass is so concentrated that essentially it takes over and squeezes the sphere of gas and goes on squeezing it while the central temperature rises and rises, and the radiation can't get out fast enough, to the point where nuclear fusion reactions jump in. So for a while, the nuclear fusion reactions, the conversion of hydrogen into helium, halts the collapse of this sphere of gas. It brings the force of gravity to a halt. It balances the force of gravity because energy is released here that maintains the temperature, that maintains the pressure, that anywhere in this object exactly balances the inward squeeze of gravity. But of course, energy gets out, that's why the sun glows, and radiates away. So we are still losing energy from this system. And of course, eventually, we start to run out of fuel. Already, the density is increasing in the center of the sun due to hydrogen being converted into helium, and we are already at the point where, for that reason, the sun is about 30% more luminous than it was when it was first formed. It was first formed round about here, the birth of the solar system. This is where we are today, and that process will go on. We will go on using up the hydrogen, converting it into helium, until we run out of fuel in the center of the sun. The sun will then expand into become a red giant, and other sources of fuel will temporarily come into play, but in the process, the sun will get ever more luminous, steadily getting more luminous till the oceans boil. This is in thousands of millions of years' time, and eventually we believe the Earth will be swallowed up by the sun. Now, I don't want to go into details about the exact details of what happens today, because I want to make a further point about gravity and the force of gravity. The sun, of course, will have swallowed up the Earth, but shortly afterwards it will lose its outer atmosphere as a beautiful planetary nebula when it becomes a red giant, and then it will slowly fade away. Now, what I want to talk about are the more massive stars. You'll see this is a very quick gallop through the whole idea of stellar evolution. When stars are born, there are always a few very massive ones and many more that are more the mass of the sun, and those stars live their lives much faster and more furiously, and during the course of their lives they can actually start losing their outer atmosphere while they're still going through their normal internal nuclear fusion reactions. And this is a star 25 times the mass of the sun. And if we were to look inside it, we would look into the interior and we would see successive shells of hydrogen being converted into helium, creating a helium shell. Below that, helium being converted into carbon and oxygen. Below that, carbon into neon and magnesium, and so on and so forth. As we go ever deeper into the center of this star, we see that the leftover material from a previous phase of evolution becomes the fuel for the next, until we get into the very core where silicon is being converted into iron and nickel. And in order to understand what is going on and what comes next, we have something rather analogous to the whole idea of gravitational potential energy. We have the potential energy associated with the binding of the protons and neutrons in the nucleus. We know the protons have a repulsive electrostatic charge, but there is something called the strong force, the leftover force of the quarks that make up these particles, that leaks out and is able to bind the nucleus together. And so it's a bit like falling into the sun. As we bind more and more of these neutrons and protons together, we have an ever more tightly bound system, and we release potential energy as we create this tight binding. And you can see as we go from hydrogen to helium, we release quite a lot of potential energy, not so much potential, this is nuclear energy, as we get up to iron. And then we find we have a crisis, because we can see this from here to here, we release energy and so on. But when we get to this part of the diagram, we can no longer release energy by fusing. We have to actually use energy to fuse. And you will know that from your history, where we used uranium and we split it into a lighter element in order to make a nuclear weapon. And then later on, of course, we used deuterium and tritium and fused them to make an even more powerful weapon. So this is what is going to happen in the core of this star. We create this iron core, and we run into a crisis because the iron core can no longer produce energy. And so it can no longer has the potential to sustain itself by maintaining a pressure, because we have got to this point, and we can't use iron as a fuel to either fuse or split. Then don't worry about the details. Essentially, the temperature rises, gravitational potential energy takes over, presses the temperature so high so that the gamma rays become the photons, the gamma rays so energetic they completely dissociate the iron atom, and we end up with a bunch of neutrons, and we start to form a neutron star at the core, and the core collapses in about 1/10 of a second or so from something the size of the Earth to something about 20 kilometers in diameter or so in radius, and a neutron star is very hard, so the material starts to fall inwards, bounces off the neutron star, creates a shock that propagates out through the star, and this looks all very symmetrical and similar, but this is a computer simulation of this very shock, about 200 2/10ths of a second after the explosion has been initiated. The shock wave propagates out through here, creating lots of very heavy elements as the material falls inwards. The shock wave, after a few hours, bursts through the surface, and we have what is called a supernova. And a supernova completely outshines an entire galaxy. It is so luminous and so powerful. And the reason I've scooted through all this story is because I want to show you that we can understand the energetics of this system just by, again, considering gravitational potential energy. So I'm just going to put the light up a notch so that you can see me and my keys. And I want you to perform the following thought experiment. Well, here we go. So when I throw the keys up in the air, I convert the potential energy essentially into, I'm creating potential energy, or launching the keys. I'm doing work, and the potential energy is being created back into kinetic energy as the keys fall. So if I give the keys enough kinetic energy, they will more and more, they will go higher and higher. And in principle, if I was to throw them up at 11 kilometers per second, they would leave the Earth. So the following thought, we could perform the following thought experiment. We could take the Earth apart. We could launch the Earth, bits of the Earth, into space and take it far away and dump it. And so what we're doing, we're just slowly taking the Earth apart, and of course as we take the Earth apart, there's less of it, so its gravitational force gets less and less. But in principle, we could dissipate the whole Earth back out into space. And so let us pretend we can do that. We can add up the energy required. You know, each time we do a launch, we know how much energy required. And it's a fairly simple bit of mathematics to derive this simple equation, which relates the total energy required to dissipate the Earth into space from this solid, this circular thing here. And if we assume the Earth has a constant density, it's just related to its radius and its total mass. So that is how much gravitational potential energy is associated with the Earth. Now, of course, the nice thing about physics is that the inverse is true. If it takes that much energy to disperse the Earth out to infinity, which is just a very large distance, then that is the amount of energy released forming or creating the Earth. And if you want to know how much energy it does take to dissipate the Earth, and I'm using some completely new units, it's 160 hours of sunlight. So the amount of energy that the sun emits in 160 hours is enough energy to dissipate the Earth. So let us now look at some other issues. So how much energy would we create forming the Earth, 160 hours worth? How much energy did we release, gravitational potential energy, creating the sun? 18 million years worth. The problem faced by Victorian astronomers, how could the sun be so old? What possible fuel could be used that would keep the sun luminous for hundreds of millions of years? If we find it's only 18 million years worth of gravitational potential energy in order to create the sun. Now, of course, we know the answer to that. The answer to that is the conversion of hydrogen into helium. Just for the record, incidentally, these keys weigh about 100 grams or so. If you think the amount of energy I've got here is pretty small, I can catch them in my hand. If this was TNT, 100 grams worth would completely kill me and destroy me. So, you know, chemical energy, a lot of energy. But just look at this. If we took a solar mass of TNT, the energy from detonating that would only keep the sun alive for 600 years or so. So we see immediately that the nuclear energy of converting, if we converted the entire sun from hydrogen into helium, it would last for 100,000 million years. And it's only been around for 4,000 million years. So we immediately know the answer to our problem of where the energy of the sun comes from. Let us go back to our supernova now. What happened in the supernova was, essentially, in a tenth of a second, something with the radius of a white dwarf was converted into something with the radius, well, a neutron star, in fact, the core of the sun, the core of the exploding star, was about white dwarf sized and about solar mass, and we, in a tenth of a second, converted it into a neutron star. So if we want to know how much energy was released, we have to subtract that number, 2,000 million, from 1.3 million. That number is vanishingly small compared with that number. So we could say that in a tenth of a second, this amount, this is years of sunshine, was emitted in the supernova explosion. And that is essentially exactly what we find. That typically, although the description of what happens in a supernova explosion is very complex and very difficult to model, and lots of heavy elements created and all that sort of thing, it is essentially, in essence, it is just the release of gravitational potential energy. It's just what happens when I drop the keys on the table. I am converting gravitational potential energy into a bit of noise and a bit of a dent in the table. So I like these things because they are kind of simple and easy, essentially, to understand. The concept of gravitational potential energy. If I said to somebody, or in a little thing I wrote once, that if you don't believe or you don't understand gravitational potential energy, just perform the following experiment, though I advise you not to. You take a brick, tie a piece of string around it, a long piece of string, hold the string of the brick up like this, and let the string run through your fingers as the brick drops to the floor. And if you don't suffer a very nasty burn, then you haven't done the experiment properly. And if that doesn't prove what gravitational potential energy is, I don't know what does. And some other, it's quite interesting just looking at converting the whole of the sun from hydrogen to helium, which of course we don't do, would keep it going for 100,000 million years. Converting helium to iron, which is the next stage up where you have all the rest that we looked at, would only give you about a quarter as much energy as you got from converting the hydrogen into helium. And converting a solar mass of into energy through E equals mc squared gives you this 14 million. You will see creating a black hole with a radius of about 1.5 kilometers gives you about half that energy. So it's about half the entire mass energy. So in other words, gravitational potential energy is a very, very a powerful source of energy in the universe, and even though gravity is such a weak force. Now, I'm being very disciplined. I'm supposed to only speak, I'm supposed to speak for 25 minutes. I think I've spoken for half an hour. Nobody's coming to interrupt yet. So I think I'll just show that little diagram, and you ponder. And anybody who's got any questions, now's the time for some questions, if you'd like to ask some questions.